Hello dear friends, this is Dr. Diptesh Patel and I'll be teaching you Advanced Internal Combustion Engine. In today's video session, we are going to continue the chapter called Measurements and Testing of IC Engine. Particular for this video session, we are going to see the measurement of various parameters such as the brake power, friction power and heat balance sheet. So let's start with uh, the how to calculate, how to find the brake power. So we have already gone through the various types of the dynamometer, and one more that we need to cover up, that's eddy current dynamometer. Now basically eddy current dynamometer, you can see the schematic diagram over here. It consists of mostly stator, a rotor, field and a cooling system to dissipate the heat that is being generated here. So basically it consists of the stator, which is having the number of electromagnets on it, and a rotor disc that is mostly made up of the copper or steel, and this rotor disc is connected with the output shaft of the engine. Now when engine start rotating, it rotates the rotor as well, and since the rotor rotates in between these electromagnets, it produces the eddy current, uh, and these eddy currents is produced into the stator because of the magnetic flux that is been set up by the field current into the electromagnets. So now these uh, can be controlled with the help of the regulations of current in electromagnets. So we can resist the motions with the help of the current in the electromagnet. Now as I said earlier, because of these eddy currents, heat is also generated, and that is dissipated with the help of some sort of external cooling system, such as by supplying the continuous flow of water. Here the torque is measured with the help of gauge that is normally provided with the eddy current dynamometers, and the working principles are pretty much same as the others that we have seen in previous session, such as we have gone through the various absorptions dynamometer. So here we can measure the torque into the by using the same principle, and that can be obtained directly with the help of either analog gauge, or you can use some digital output as well to measure the gauge as well. You don't need to calculate these horsepower manually, but it can be measured with the help of gauge. So this is what the eddy current is. Now these next parameter that we are going to see is a friction power. So far we have seen the various measurement to measure the various instrument to measure the brake power. Now here we are going to see the friction power. Now we know that the friction, that is considered as an enemy in engineering, because it in most of the cases it is not useful. It takes away the certain amount of the power, and then after these losses, that is normally converted into the heat, and that is been taken away, that is been dissipated with the help of cooling system and the exhaust. So these all friction losses appears in the form of heat, and it also affect the cooling system as well. If the friction is higher, then there would be a chances of much more heat that would be generated, and therefore we require the effective cooling system as well. Furthermore, friction power, we know that the friction power is the difference between the indicated power and the brake power. Let me just remind you again, just revise the topic again, that indicated power is the power that is being generated into the combustion chamber, while the brake power is the power which is available at the output shaft. So since we know that the indicated power is much higher uh, as compared to the brake power, because the brake power is less, it due to the friction that is being generated, that is being occurs into the IC engine because of the various motions, relative motions of the various components into the engine, and therefore it consumes a certain amount of power. So the difference, if you if you want to calculate the friction power, then we can say it's a difference between indicated power and the brake power. And therefore, if the friction power is much higher, then in that case the overall availability of the brake power would also be lower. So overall aim of an engineer is to reduce the friction power as low as possible. Since we can reduce the overall brake power, we can enhance, sorry, we can reduce the friction power, we can enhance the brake power, and therefore the brake specific fuel consumption would be also lower. So this is what the friction power is. Now how do you measure the friction power? Now there are various methods that can be used to measure the friction power, such as Williams line method, then Morse test, or simple motoring method. In simple motoring method, the engine is operated with the help of the motor, electric motor, and it is run for the little while to maintain the constant oil pressure, to maintain the constant cooling system or the temperature of due to the frictions. And then after certain period of time, the power that is being delivered with the help of the motor is measured, and that would be friction power. So this is how you can measure simply the friction power is, and that is known as the motoring test or motoring method. Another one which is quite reliable as compared to this one is a William line method. Now this method is having another name as well, and that is also called the fuel rate extrapolation method. Fuel rate extrapolation method. So here basically it's a kind of the value that is being plotted into the graph. Here in y-axis, the values of fuel consumption is noted, while the x-axis is having the brake consumptions. So basically the graph is plotted uh, in between the fuel consumptions and the brake power, and it is drawn, the graph is drawn over it. Then after, it is extrapolated onto the negative side of the brake power. It is extrapolated into the negative side, and wherever these line intercept to the negative axis is taken as a friction power of the engine at that particular speed. So here we are going to see, as you can see, the graph is shown over here. On the y-axis vertically, the fuel flow rate or the fuel consumption rate is described, while on the x-axis you can see the engine torque. Now it is the engine torque and the fuel consumption rate is been measured here, with respect to the various torque, and then after a line is drawn over the Williams line, and then after it is been taken into the negative side, and wherever it intersect with the negative side is taken as the friction power. So you can see the friction in torque is been described into the negative side of the engine torque, that is been taken as a friction torque or friction power. So William lines method is also been easy, but there are certain drawbacks of the William line methods. The main drawback is that in long distance, for the long distance to be extrapolated from data in between, let's say 5 to 40% toward the zero line of the fuel input, right? It is not possible that for the longer distances. And the accuracy is also another issue for the William line method, because the directional margin error is always occurs, and therefore that is this error is always wide, and therefore the graph is not exactly linear. So therefore there is always a questions about the accuracy of the William line method. So this is how the William line method works. Next test is about the Morse test. Now Morse test is one of the most accurate method to measure the friction power as well as indicated power. You can measure the indicated power by using this one as well. And once, like as I said, there is a relations between these three powers: indicated power, brake power, and friction power. You know that the difference between indicated power and brake power is known as the friction power. So any two of these values parameters are known, you can find the rest. So basically Morse test is being carried out especially for the multi-cylinder engine. You cannot carried out the Morse test for the single cylinder engine, because here we need to cut off the each engine one by one, right? So In most tests, first of all, the engine is run at required speed and output is measured. So like uh, engine is started with the like decided speed, and once it achieves that, the throttle is adjusted and the output is measured. Now once the output is measured, then after, each cylinder is cut out one by one, right? If the cutout system for the cylinder is different for the petrol and diesel engine. For petrol engine, we can short the spark plug, while for the diesel engine we can disconnect the line, fuel flow line of the injector, or we can like we can stop the flow of the fuel through, which is going through the into the combustion chamber through the injector. So you can either short spark plug or the injector for petrol engine and diesel engine respectively. So this is how you can cut out the uh, engine cylinder. Now once the one engine is cut off, one cylinder is cut off, the engine is being tested again. So obviously we know that the power availability of the power and speed would be lower, because only, like let's say if it is a 4-cylinder engine, then only 3 cylinder will be working while one would be cut off. And even the friction power would be same, because like all of the 4 cylinders are moving up and down into the cylinder, so the friction would be same as it was in a first test, but the power availability of the power of the one cylinder would be reduced. So the speed, both speed and the power will reduce, while the speed is adjusted, and that is mostly kept same as the previous test by adjusting the throttle. And thereafter the difference between these two are the measured, which describe the let's say indicated power of the particular engine. And this test is repeated for each and every cylinder, and this is how you can measure the indicated power of each cylinder. So Morse test is one of the reliable way to take the, or to find the various parameters such as indicated power, friction power, or even brake power, if these tools are known. So this is one of the accurate and important method to find the parameters. Now let's move forward to the heat balance sheet. Now heat balance sheet is very important component. It's a very important component to measure the performance of an IC engine. And here these are the various parameters that we need to look while we are designing the heat balance sheet. So let's say, what are the different components of the heat balance sheet? The first one is heat equivalent to effective work of the engine, or it is also known as the brake power. So whatever the brake power which is available from the engine is being described here, and that amount of heat that is being utilized to generate the brake power. So that's why it is known as heat equivalent to effective work of the engine, whatever the work that is being produced by the engine. Second component is a heat rejected to the cooling medium. We know that the since we provide the cooling system into the engine, it also carried away certain amount of heat, because we don't want to like damage the different components, and sometimes the heat into the engine would go very high. So therefore the cooling system, proper cooling system is required, but it also consumes a certain amount of heat that might be utilized to generate the power. So the second component is a heat rejected to the cooling medium. Third component is a heat carried away from the engine with the exhaust gases. We know that the certain amount of heat is also being wasted into the exhaust gases, and that is being emitted into the atmosphere. There is no any way that we can utilize it again. So therefore, like even in today's world, a lot of research is being carried out to how to recover this waste heat which is coming out from the IC engine. So the third component is a heat carried away from the engine with the exhaust gases. And the last one is unaccounted losses. Now there are various losses that occurs, like such as the heat transfer by radiations and the convections, that is, or the heat transfer due to the leakage, or heat may be escaped through the leakage. These are the known as the unaccounted losses, and these losses are also higher. So we also need to work on it. Now once all these heat resources are known, like we know that how much amount of heat is required to be converted into the work, how much heat is lost in cooling medium, in exhaust gases and other uncounted losses. We can design the engine perfectly. We can optimize the engine performance, but before we need to work on it, we need to find out the heat balance sheet. So here these are the various formula which been given here to calculate the heat balance sheet. First thing that we need to calculate is how much amount of heat that is been applied into the engine, and this can be calculated by mass of flow and calorific value of fuel. So heat supplied can simply be calculated by using the formula called MF into CV. Now here heat that is being used up, right? On the other hand, we need to put the amount of heat that is being used up by the various components. So the first one is heat equivalent of brake power. So here we need to calculate the brake power, and the simple formula is 2 pi and T divided by 60. You can use this formula to calculate the brake power if these variables are known, right? So this is how you can calculate the heat equivalent to brake power. Then heat carried away by cooling system, and the formula is CPW into MW into TWO minus TWI, where CPW is specific heat of water, MW is a mass of water, TWO is a temperature of water at outlet, and TWI is a temperature of water at inlet. So this is, you can calculate the how much amount of heat that is been lost in cooling water. And the last component is a heat carried away by exhaust gases, and the formula is again mg into cpg into tg minus ta, where mg is a mass of gas, cpg is a specific heat of gas, tg is a temperature of gas, minus ta is a temperature of air. So these would help us to find the various components of the heat balance sheet, and this is how we can design the heat balance sheet. Now we know that there is a one more part in the heat balance sheet which is known as the unaccounted losses, and as I said earlier, the unaccounted losses are the one which is the amount of heat that is been lost in because of the leakage of the gases, or these lot heat is lost due to the convection or the radiation. And furthermore, certain amount of power is also required to run the accessories of the engine. We know that we need to run the fuel pump, camshaft, then many other equipment such as water pump as well, or the radiator. So certain amount of the power is being consumed by these all component, these all accessories, and therefore this is also considered as a unaccounted losses. So whatever these cannot be measured precisely is known as the unaccounted losses. And if we want to calculate the unaccounted losses, then we can find the difference between the heat supplied minus heat equivalent to brake power, heat lost in cooling system, and heat lost in exhaust gases, right? So if we get the difference of these, we can find the unaccounted losses, right? So let's say if we can calculate the heat supplied by calculating QS, by calculating MF into CV, we can get, let's say it's 100%, then we can minus all these remaining three component A plus B plus C, and we can minus the summation of A, B and C out of 100, we can get the unaccounted losses. And like once these all values are known, that can be that can be formed into the tabulated table, and that table is known as the heat balance sheet. So this is how we can calculate the, or we can design the heat balance sheet for any particular engines, and we can optimize its performance like by checking various losses that is occurs into the engine. So this is all at the moment. If you have any doubt, you can write down in the comment box. Thank you very much.